documents, and I want to talk to you about serverless. So the problem in a nutshell, docx to PDF conversion is CPU intensive, and what I mean by that is that if you've got a single core and a single document to convert, it'll utilize it, pretty much 100% until it's done. So if, for the sake of argument, that conversion job takes 10 seconds, if you wanted to do it twice, it would take 20 seconds. So, of course, any particular conversion job is going to depend on the complexity of the document, and it's not just the number of pages, but the sorts of things you have in it. I don't know whether anyone was in the Word document rendering presentation there before, but basically you can't render page 300 until you've done all of the pages before it. And so it's very hard to sort of divide it up into parallel jobs and do, each page in parallel. Word's Word to PDF output is a very good guide to, how efficiently this stuff can be done. You can try a 10-page document in Word and see that it's relatively quick, and then you can try a 1,000-page document in Word and see that it'll be, 10 or 100 times slower, depending again on the content. So if you've got a lot of PDFs to produce, you're going to need lots of cores, and that means lots of servers. The easiest solution, of course, is if you've got this sort of load to have enough CPUs to do the whole thing, and they're all hot and ready to go. That's expensive, and so what people try to do is to scale up as the load changes. The problem with this approach is that each of these spots here is over capacity that you're paying for, and this is sort of a serious problem that you're probably going to be filling out reports to management as to why you screwed it up. So what's the solution? Well, the solution is serverless. Basically, somebody else runs the servers now. You just got to imagine there's a bank of servers there, and as long as your job is one that can ramp up quickly enough, i.e., assuming that the server's there, as long as it can start fast enough, you're kind of good to go. This is a familiar graphic. It's also a little bit misleading in this scenario. It's misleading because it kind of suggests that you evolve this way, whereas in fact what's happened with these technologies is that they sort of feed on one another. I've put some dates down here. I've put for virtualization that KVM came to Linux in 2007. Obviously that's not the beginning of virtualization. I was using VMware in '99, and there's probably a few people who've used IBM virtualization systems way before that. Nevertheless, that was kind of a key thing for virtualization. A key thing in cloud computing, of course, is EC2 in 2006. Containers, well, Docker and Kubernetes. Serverless, it's sort of interesting to have here because whereas virtualization is a particular approach and containers are a particular approach, well, serverless is sort of an idea, and it's an idea that relies on these other things. So if you take Lambda, for example, well, in 2018 they introduced this thing, Firecracker, which is a sort of virtual machine that starts up really fast. And so they're bringing this kind of virtualization, new approaches to virtualization to the serverless stuff. This is probably a more sensible way to communicate what serverless means, and that is that for developers you're not thinking about servers. You're thinking about the functions that your application performs and how to put an application together out of smaller building blocks. There are some things on that chart, like, for example, that your containers live for minutes or hours. Well, we've got containers that live for weeks or months, so that's not necessarily strictly true. I would say with virtual machines that one of the advantages that should be listed there is that they're more secure. Nevertheless, for a developer, what you're doing is you're creating your functions, and this is certainly true. You want them to deploy fast, and then they're going to live for just as long as is necessary. So serverless is kind of the big thing. It doesn't matter whether you use AWS, Azure or Google, you'll find serverless technology there. IBM and Oracle also do it. And for people who might be wanting to do something in a more open kind of a way, there's various approaches to doing it on Kubernetes. This Knative thing is sort of the newest platform for doing it. And then there's also this serverless framework that allows you to basically write to that and then deploy to Lambda or Azure. I don't really want to get bogged down in this slide. What I would say to you is that anyone who's getting started with serverless, if you've already got a relationship with one of these platforms, just become familiar with how things work there, and then move on. You'll find that there are common concepts that work across the whole thing. So basically you have a function, it's written in some kind of a language, it needs to be run. So how does the function know when to run? Well, there's some kind of trigger event that kicks it off. The scheduler stuff just happens in the background, you don't need to worry about that. Your job as a developer is to write your function in whatever language you like and then package it up. On Lambda, you package it up basically as a zip file. Some of the other platforms you can deploy straight from Git. All of the platforms support JavaScript, and then what other languages and approaches they support is kind of platform dependent. Very important is this trigger event thing. So how does your function get started? On Lambda, the trigger events include just a typical REST API. S3 is Amazon's place for storing documents or files. You can also trigger it with a message, and step functions I'll come back to. This is important because when we're talking about Word documents, they can obviously vary in size from tens of kilobytes to tens of megabytes, and that's not going to work. On Amazon, there's limits as to how big your post body can be, limits that Lambda has, and if you're using REST, it comes via a thing called an API gateway, and that's got limits as well. So you can't rely on somebody just posting a document and it getting through these gateways because it might be too big. So the approach we've taken is the document's going to be on S3, and it's just a matter of how you tell the function what the document is. So you can use an SQS message to say, hey, get document XYZ from S3. Or, in fact, in Lambda, you can also have an S3 trigger event. So anytime a document gets put onto S3, it sends a message to Lambda saying, hey, here's a new document, process it. So this is kind of, I guess, one of the key slides in the presentation. This is showing processing 200,000 PDFs in 10 minutes on Lambda. So each of the dots represents a document. You can see that most of them are down here. The time scale on the side is milliseconds, so that's 10 seconds and that's 25 seconds. So most documents process in around about 1 second. Some of them take a bit longer. And then you see there's another whole bunch of dots here up around the 9 or 10 second mark. The reason for that difference is that a new function had to be kicked off. So if there was already a function running on Lambda, it can be reused. But if there isn't a function that's available and running, well, Lambda has to fire up a new instance for us and then execute the function. And it takes 8 seconds before it can do that. Now, it's important to note, I suppose, that it doesn't always take 8 seconds for Lambda to launch a function, as in other people's functions. It takes 8 seconds to launch ours because it's a pretty big function. There's 30 megabytes of code and 30 megabytes of font, and you've got to unzip it, and that's how long it takes. So our 200,000 PDFs got generated actually using 591 instances, and in the Lambda console you can kind of see how those things were kicked off. So if we kept going, it probably would have kept creating more functions up until the limit of the standard limit, I think, is 1,000. But as it turns out, for the load that we fed it, 591 was enough. So it's pretty cool, actually, particularly if you compare doing this to using, a cluster on AWS, where you've got to, you're responsible for the scaling yourself, and if an EC2 instance has had to start up in order for you to run your function, well, now you're talking tens of seconds or a minute, right? So the fact that things start really fast is great, and the fact that you don't have to worry about this auto scaling is great. It's funny, I can't see the colours here, but over there, I've said better, faster, cheaper. Well, it's certainly cheaper, right? The cost for those 200,000 PDFs, well, it took 175,000 seconds, which cost approximately $5. In fact, it costs nothing because that's within the free capacity that Amazon gives you every month. Obviously, it's faster. I should have written easier. There are some things that aren't so good. If you tell your developers to start doing this, there's a learning curve. They've got to come to grips with a whole new approach. Things are kind of moving relatively quickly in terms of the technology and the tools that are at your disposal. And so, if you're trying to find a single document that tells you the perfect way to do everything, well, it probably doesn't exist, and if it did, well, it's out of date in a month's time. And also with this Lambda stuff, it's kind of a pain to look at the logs, right? Because if you've got a function or an application that's made up of 5 different things, and it's going that you've got to follow through and find out where the problem was. And if you're looking at logs on Amazon, and well, let's say you've done 200,000 PDFs, finding the logging that relates to the problematic document 1001, well, it's painful. People make tools to make it easier, but compared to just grepping through a log on your local workstation, it's not that much fun. So, a couple of slides on what's required to actually do this stuff. So the first thing is you've got to have code that's going to run on your platform of choice, and here I'm talking about Lambda. As I said, lowest common denominator is Node.js, that runs on Lambda and Google and Azure. So in our case, we took a C++ code base, which is our stuff, The way we do PDFs is using Skia, Google's Skia library, to create the PDF, but we took this C++ code base and converted it to WebAssembly using mscriptum, and you can run WebAssembly in Node.js. As this picture shows, there's sort of two things you can do with WASM. One is run it via Node.js, which is what we do on Lambda. The other is run it in a web browser. So we can also do our PDF conversions entirely client-side, although it's the case that you have to download that payload that I was mentioning before. So if you've got a web browser user who's only going to be converting one PDF once off, it's probably not a great approach. But if you've got a bunch of people who are going to be doing it again and again, well, doing it in the browser works quite nicely. I've got another slide here just evangelizing how great WebAssembly is. This PDF stuff is sort of a byproduct of our reason for being at Native Documents, which is editing Word documents in the web browser. And so we run our entire code base in the web browser using WebAssembly, and it works really well. If you look at sort of the stats that come out of Chrome, this WebAssembly approach is really quite memory efficient as well. As was mentioned beforehand, you know, in the world of Word documents, to render the 300th page, you've got to get all the way down there. And so when you open a Word document in a web browser, everyone can display page one. The question is, what happens is you sort of hit the page down button and get to the bottom of the document. And, well, these figures are probably too small to see, but the memory usage for this RTF specification, if you scroll to the end in Word Online, well, you're using 680 megabytes of JavaScript memory. We use less according to Chrome. So I've kind of spent 2 pages here telling you why WebAssembly is wonderful. It really is ready for prime time, and it's a great solution if you've got C code that you're trying to repurpose for using in the web browser. In our case, it's actually not necessary, because on Lambda you can use what's called a custom runtime and run your C code directly. Provided it runs on Amazon Linux, you can run it directly. And so if I go back to that chart where I've got this 8 seconds to launch an instance, this is in the context of using the node approach. If we were doing it natively, it would be a lot quicker. But it turns out it doesn't matter for this sort of batch application, right? So the path of least resistance is to run it within Node, but if you need faster performance, well, you can use a native runtime. So now a few slides on, what a serverless type application might look like, and this is kind of coming back to the stuff Dov was talking about earlier today. Sugford invoices. Sugford PDF invoice is a PDF document with a bit of XML embedded in it. And so how do you go about creating one of these things? Well, the way I do it is I'd start with my invoice in Word, or in an invoice template. I'd use that template with the XML to create what I call an invoice instance. Now I convert it to PDF. That's just a normal PDF. To make it a Sugford one, you've got to add the XML message back in, and you can do that, using Mustang or something like that. So here we're looking at an application that's 4 different steps, right? Combine them to make the Word document. Second one is to make the PDF. Third one is to take the invoice and the PDF and convert it to a Zugford one. And fourth is to email it to the end customer. So how do you join all of these things together to make an application? Well, the easiest way is to just rely on those event triggers that I was mentioning before. So for example, if you were to drop this XML invoice message into S3, that could trigger this conversion. If you save this into an S3 bucket, that could trigger that, and so on. It's not very deterministic in that it's just, how do you keep track of who it's going to get emailed to in the end unless you can associate that in the document somehow? So a better approach is perhaps to use SQS messages, right? So now you have a stream of messages per customer, for example, and the first message says create this invoice instance. The next when that's finished, it sends a message saying I'm done, now make me a PDF, and so on. But the logic is sort of hidden in the functions that way, right? No, there is nowhere to actually look to see this is how the application works at a sort of a conceptual level. So in a moment I'll come back to a better way to do that. First, I just wanted to sort of say, well, wait a minute. You brought me to the presentation on the basis of millions of PDFs, and now you're talking about Zugford e-invoices. Are they really high volume? And the point I want to make is that this serverless approach works equally well whether you're dealing with just a few documents occasionally, as instead of having one server running continuously, you've just got this function that happens every few days, as it works with the millions of documents cases. It's just that in the eStatement case, I think, is the best example, because if you're doing all your processing once a month, well, that's the prototypical case of a huge workload and the rest of the time things being idle. So getting back to how you wire these things together, in the world of Amazon, they have a thing called a step function. And so this is a simplified version of a step function that one of our customers uses. It's basically the same thing as I just showed you, merging data together, generating a PDF, and then sending it. But this is sort of a screenshot of the Amazon interface. You get this sort of visual way of composing functions together. And along with the visual impression, the JSON that corresponds to it. And so if you look at any one of these, for example, it says pre-merge validation, and when that's kicked off, it's this particular Lambda function that does it. So here the sort of structure of your application is abstracted and made visible. I got a warning that I'm running out of time, so I'll skip quickly over this next one. This is sort of the Salesforce interface that our customer iDialog had that corresponds to the step functions we just saw. They replaced an old very server-heavy architecture with this serverless thing, and in the context of Salesforce it works great. Lessons learned. Faster can sometimes be cheaper. So I mean that in two senses. Firstly, that we've created 200,000 PDFs in 10 minutes. But secondly, that in Lambda you can choose how much memory is allocated to your function, and sometimes, and because you don't have a choice of how many CPUs you allocate, but let's say for the sake of argument you allocate one gig of RAM, that comes with 4 cores. You allocate 2 gig of RAM, you get 8 cores. It turns out that sometimes you're better off ramping it up to the max, so you get the maximum number of CPUs. It processes quicker, and because they charge per millisecond or per 100 milliseconds, it works out to be cheaper. WebAssembly, I won't talk about that anymore. This whole approach of making it easy for customers to run their conversion jobs on their own infrastructure gets around this whole problem that, well, most of the people who talk to us anyway seem to have of, well, we don't want to send our sensitive documents off to some API in the sky. So, well, the answer is run it yourself. You do need, from a customer perspective, to make sure that you're using a vendor that has a serverless ready licensing model, right? If they're going to charge you per core and suddenly you're running 591 of them, well, there's a problem. This is sort of interesting. You're always going to have a bottleneck, right? So if you move the PDF conversion to serverless and it all runs nice and fast, well, whatever's making your end-to-end application slow is now going to sit somewhere else. And okay, well, you move that to serverless as well, and so it goes on. For the purposes of putting this talk together, the challenge was kind of generating that load of 200,000 documents. How do you feed them to Lambda fast enough to, produce the output quickly enough? I think I'm done. I've just got a thank you slide. We've got some code at GitHub/native documents if you want to try any of this stuff. Thank you.
Thank you.